Yeah, welcome to Calculus 1, class number 2, because lecture. We are going to talk about infinite limits today, and we're going to define some very interesting concepts. So let's start first with explaining what the infinite limit is. So infinite limit is where the answer is either positive or negative infinity. And the short way to say that in math notation is that the limit x goes to a of f of x is either going to be positive infinity or negative infinity. So this would be infinite limits, meaning the answer is infinity. The quickest example of this would be, let's say, limit x goes to 0 of 1 over x squared. And the answer for that is infinity. Why? Well, we are going to look at the graph of the function, and we'll see that the limit as x approaches 0 minus, which is from the left, of 1 over x squared is positive infinity, and also limit that approaches from the right is positive infinity. Since they're both positive infinity by the theorem that we covered yesterday, left limit and the right limit have the same value. The overall limit is that value, which is positive infinity. So it's, I think, straightforward to understand what we are doing. Now, why is this so important? Well, this is your definition for vertical asymptotes. See, in pre-calculus, you learned something about vertical asymptotes, but that is incomplete. Today, we learn the actual theorem that covers all cases of vertical asymptotes. So, we would say that the vertical asymptotes occur when limit x goes from the left, right? X goes to a from the left of f of x is positive, negative infinity, or limit f of x, x goes to a plus is positive or negative infinity. So we use one-sided limits to figure out whether there is vertical asymptote or not. Now, looking at the example above, clearly there is a vertical asymptote at y-axis, which is x equal to 0, as the limit for that was infinity. This is what we are doing in this section. It's a very short section, right? We only look at this. These are the concepts. This is the theory. And now we just need to do a few examples, find few vertical asymptotes, and we're done. Yes?
Wait, underneath the limit of x, it's x approaching the negative side?
Yeah. A minus, which is limit approach from the left. A minus is the notation from the left, and a plus is approach from the right. Now, in both of these cases, from the left and from the right, when we get one of these infinities, the limit still does not exist. We label it as limit is infinity or negative infinity, but limit does not exist because, in the sense that it's not a finite number. So limit exists when it's, let's say, a half or a 5, then limit exists. If the limit is infinity, or if the limit does not exist, we label them all as does not exist. But in the case of getting these infinities this way on the one-sided limit, we know that there is a vertical asymptote in that case. So that is the definition for vertical asymptotes. So now, let's take a look at the limit of 1 over x as x approaches 5. What would that be? 1/5. Exactly. Right? Remember the problem from last class? Just plug it in, right? So if we are looking at the limit of 1 over x, and x is any other value than 0, then we can simply plug it in and we will have the answer. So what happens in the case of limit x goes to 0 of 1 over x? Well, for that one, we will look into the left and the right limits, and we will decide from there. So first we're going to take a look at the limit x approaches 0 minus, which is from the left, and the answer is negative infinity. Now this answer alone implies that there is a vertical asymptote at x equal to 0. That's enough. Just to see that any one of the one-sided limits is infinity or negative infinity is enough to claim that there is a vertical asymptote at that value. Now we're also going to check the other limit. So limit x approaches 0 from the right, which is 0 plus, and that one is going to be positive infinity. Now that also says vertical asymptote at x equals 0. So both of them. But if you combine these two results, what is the limit as x goes to 0? Does not exist. Why?
Because one goes to positive infinity.
Very good. One goes to positive infinity, the other goes to negative infinity. They do not agree, therefore limit does not exist. So we need to distinguish between all of these different phases. We have limit from the left, separate from limit from the right, but together they tell us about vertical asymptotes, and then together they tell us about the overall limit. And I think on this example here you have all possible combinations that you can get within any problem. If the problem can be computed without calculus, well, then you use pre-calculus, which is plug it in and you get the value. So the meaning of this expression is exactly the pre-calculus concept when you are plugging phi into equation. So when nothing weird is happening with calculation, there are no zeros in denominator or anything like that, we have a simple pre-calculus 1 calculation where we plug in 5, we get 1/5, which is 0.2, and that's the y value. So technically, this one is computing function values at that value. We have to involve calculus when you try to plug this in, you get 0 in denominator. In that case, we saw earlier, yesterday, that some limits will actually have a finite value and some limits will not. In this case, this is the one that doesn't have a finite value. So we calculate left and right limits immediately by looking at the graph. So if I'm approaching 0 minus, that means from the left, you can see that as you are going x-axis, as you're going towards 0 from the left, the function goes down to negative infinity. And if we are approaching from the right, which is approach from the right, the function will go up into positive infinity. These two are not the same. Therefore, by the theorem from yesterday, left and right don't agree. Overall limit does not exist. Yes?
If we didn't have like a graphic calculator, so we would be able to see the graph, how would we know that the one equals negative and the negative is positive?
Okay, so to answer that question is you will either learn all of the basic graphs that are supposed to be common knowledge for calculus 1. If you don't have that knowledge, you will actually have to graph it using the points. So you assign x value, compute y's, you have the points and you connect them. You can see 1 over x, you can graph that by saying, give me x to be -3, -2, -1, 0, +1, +2, +3. That will give you boom, boom, boom points, right? And then you connect those, and you connect these, and you have the graph. That is the middle school way of graphing, and it works on any function under the sun. You will have access to a scientific calculator which can compute anything, including e's and sines and cosines. But since the basic functions are all learned in pre-calculus, we do expect students to know, and that was the reason why NJIT made the push also for no graphing calculators, so that students actually learn basic graphs, basic shapes, because it's important later on for regression and some other things when you actually start working. That's the stuff that computers can't do today. You know, education is kind of backwards. We spend too much time on calculations and very little time on application, where it should be the other way around. The important things that are not stressed out. A lot of time in pre-calculus is wasted on how to compute things rather than actually learning the functions. So that's the reason why majority of the students don't know the basic things, like the shape of the graph, but they know how to compute it. Well, it's not important to know how to compute it because computer can do it. Computer can't set it up. Computer can't do certain things that we can. So that's the problem. Everything is backwards. So yeah, I hope this answers your question. Yeah. All right, good. So learn the basic functions. Did we review that list? Yeah, we did, right? Let me just check on the first. So the pre-calc review. This will all be uploaded after the class today. Let me just check. I think I had the, yes, there it is. Basics of graphing. So all of these that are on this list are understood that you guys know eyes closed in Calculus 1, N2, N3, and so on. So if you have issues with that, practice, and then we'll review when we need to review, do more work. Okay, let's take a look at next example. So in pre-calculus 1, you were faced with a function, let's say f of x is equal to 3 over x plus 4. Are there any vertical asymptotes there? At -4. So as you can see, pre-calculus 1 still works, right? You know from pre-calculus 1 that the vertical asymptote is at x equals -4. By the way, I just need to make sure that you are not doing this. If you write VA equals -4, that's just garbage. It has nothing to do with anything. That notation does not exist in mathematics. Don't do that. Equation of the line is x equals -4. So vertical asymptote at x equals -4. Why? Because that would make 0 in the denominator. Now, let's prove that. Well, all I need to do is to say limit x goes to -4 of 3 over x plus 4 is equal to what? Well, we know that we are supposed to check for vertical asymptotes any of the one-sided limits. So we are going to check, let's say, approach from the left. So x approaches -4 and a little minus on top, telling us that it's from the left, of 3 over x plus 4. Now, as I said, the first thing you do is you try to plug the number in. If it works, you're done. If it doesn't work, then you have to resort to other stuff. So you're looking at this and you say, well, if I plug in -4, I get 3 over 0, so that's not going to work. And then you say, well, I can graph this because it's a basic graph which is just shifted a little bit, so it's nothing crazy. It is x plus 4, which means that we are shifting it left 4 units. Very good. So I'm just going to say that this is -4. And we have 1 over x, which is 3 over x, but it's 1 over x, the same thing. So we have the graph that looks like this. Shifted 4 units to the left because it's x plus 4. And if you look at the left limit, it goes to -infinity, which means, since the limit at -4 is -infinity, means that the -4 is the vertical asymptote. So that is the proof. Just from here, we see that there is a vertical asymptote at x equals -4. So that was it, believe it or not. Now the over limit will not exist, and the approach from the right will be positive infinity, so everything like the previous problem. We just need one of them to show it's infinity, and we have the vertical asymptote there. So pre-calculus is confirmed. One more example of these. So how about f of x is equal to, let's say, x minus 5 over x squared minus 25. What's happening there? At negative 5 and 5. So vertical asymptotes at x equals negative 5, x equals 5. Would anyone agree, disagree, add or subtract anything? Yep. No vertical asymptote there. Pre-calculus cannot detect that. So we are very careful which questions we are going to ask in pre-calculus, because you don't have a tool in pre-calculus to test for this, because we don't learn limits there. So question like this will not be in the pre-calculus book, because setting denominator equal to 0 is not sufficient. However, it's necessary. We are still going to set denominator equal to 0, but the numbers that you get here are candidates for vertical asymptote. And then you have to do the limit to see if they are vertical asymptote or not. So you know what I'm going to do? I'm going to just do this. I'm going to leave it as x equals to negative 5 and x equals to 5, and say these are the candidates, right? One of these two is trump. Never gets old. All right. So what are we going to do? Let's test it and see. Remember, any of the one-sided limits. So let's go with negative 5 from the left. It really doesn't matter. X minus 5 over x squared minus 25 is equal to what? We are going to do exactly what Lawrence said, and that is negative 5 from the left. We're going to factor the denominator into x minus 5, x plus 5. Now, this is from the previous section, solving limits. And now what do we see? We see the limit x goes to negative 5 from the left of 1 over x plus 5. Now, what is that? Well, looking at the graph, where is it shifted? Left. So this is where the negative 5 is. We have a good old 1 over x shape. And we see that as it goes to negative 5 from the left, the answer is negative infinity. So, yes, vertical asymptote at x equals negative 5. Good to go. Let's check out 5, see what's happening there. Any one of the limits, left or right, doesn't matter. So what's happening at that limit? Limit x approaches 5 from the left of x minus 5 over x squared minus 25. Now we know that, again, it's going to factor and it's going to cancel. So we're going to end up with the limit x goes to 5 minus, and I have 1 over x plus 5 like this. And what's the answer here? 1/10. Is that an infinity of any sort? No, right? So not an infinity, which means not a vertical asymptote, not a vertical asymptote. Not a vertical asymptote. Now what I'm going to do is I'm going to now graph this function, and you will see that this function really has only one vertical asymptote, and at the other one, at 5, we are going to have
No, I didn't have the answer.
what are we going to have? What are we going to have at 5? No vertical asymptote at 5. What is at 5? A hole in a graph, a hole at 1/10. Yes?
So with these types of problems, you always want us checking for a vertical asymptote because it seems like kind of backwards if we should check the infinity first, right?
Well, what do you mean check if it's infinity first?
Because, like, on the bottom part that you did, so it was not an infinity, so it's not a vertical asymptote. So I'm saying, like, should we be doing that first to check that first, or do you want us to solve and see if there is a possible vertical asymptote first?
You have to actually first find the candidates, right? You have two candidates to vote for them, right?
Yeah.
So you first solve the denominator equal to 0 to give you the candidate, because you have to have those so that you can set the limit to those and check.
Oh, okay, so you would not be able to find that, right?
Yes, you can't do this part because you don't know where this goes to, right? So this -5 comes from the list, which came from the set equal to 0.
Okay.
Awesome. All right, let's go to Mathematica real quick. Take a look at the graph of this. It's going to look, actually, what's the graph? The graph is this with a hole at 5. That's what it is. But let's show it. So graph x minus 5 divided by x squared minus 25. And as you can see, only one vertical asymptote. This is negative 20 over here. So negative 20, that means negative 15, negative 10, negative 5. You see that negative 5, there is a vertical asymptote there. And here's 5. No vertical asymptote. Now, it is a little bit, it's hard to see that there's a hole there. Maybe if we zoom in. Yeah, it's not visible. Yeah, it's not displaying it, but right there, there has to be a hole. Now, if you use your TI-8384 and you graph it, it will actually have a missing pixel there if you use the graphic tool. Yes?
What's the difference between the two graphs on the
What two graphs?
well, if you zoom back out, there are two graphs. One is not one.
Let's take a look. The difference between two graphs. Oh, this one just shows a part of the, just shows the part. You see it goes from negative 5 to 10, shows one branch of the function, and this one shows both. Well, now it's zoomed in so you can't see it, but. All right, good. The most important part over here is to realize that we do have only one asymptote showing. Only one asymptote is present. Now I just want to point out that if the numerator was anything other than x minus 5, let's go with 3, because in this case it would not, oops, have to do it here. In this case, it would not cancel. Then you would have two vertical asymptotes. Because remember, x minus 5 cancels with one of the x minus 5 because 25 factors into negative 5 and positive 5. And now that you have negative 3 on top, it doesn't cancel with anything. So there are two vertical asymptotes now. There is one here and one there, 5 and negative 5. So question like this is okay to be in a pre-calculus because you set denominator equal to 0, you get two different values, and both of them are vertical asymptotes, you're good to go. Where in calculus, we can also look at the other one and distinguish between the hole in the graph and between the vertical asymptote now because we have limit to prove it. So now going back to our example, if the one-sided limit is infinity, we have a vertical asymptote. If one-sided limit is a number, in our case 1 over 10, it is a hole in the graph. And that hole is at 5 1/10 in this case. And believe it or not, the section is done. It's just whole variety of different problems that involve maybe e to the x, maybe tangent, maybe, but there is nothing else concept-wise that we can add. So let's take a look at one of the homework exercises. See if that can bring in anything new. The whole, I'm going to actually turn to homework page and show you in the book what they have. So look at this. 5,000 problems that are all the same. It's just a whole bunch of these things that you have to factor, cancel, and then just, right? Set denominators equal to 0 to get the candidates and then check limits. So looking at this one, right, it has x minus 2, so the problem value is 2, and there it is, 2 over there. Can this factor so that 2 can be canceled? If yes, then no vertical asymptote. If no, it is a vertical asymptote, and so on. All of these problems are exactly the same problem I did in class, where the answer is either a vertical asymptote or a hole, and it's just different numbers. So you just keep actually practicing algebra here in terms of factoring and canceling. Yes?
So the situation where you have a hole in the graph would be when you factor out x minus 5, for example, but there's also an x minus 5 in the numerator. So, okay.
They cancel, and when they cancel, you try the limit procedure. If the limit comes out to be a number, that's the hole. The number that you get at the end is the y value for that hole. Okay. X value is obviously the input for x goes to that x value, right? Okay. So x comma y, that's where the hole is. And as you can see, all of the problems are the same. There are some concept questions before that, but technically that's the homework. So shall we look in one of these? If you have something that looking at the homework page you don't like, maybe we can do it now, so I don't have to put it on a test.
You don't have to run the test.
Yeah. 24. Of course you're going to ask about 24. No, that's hardly the last one because there is a next page with a whole bunch of these, and then the next page. So yeah, it goes all the way to 55. So 24 is kind of halfway. But let's take a look at 24 because you like it so much. So 24. We have, let's just write it as a function, find the candidates and then just check limits rather than solve 4 problems they gave us. So it's x cubed minus 5x squared plus 6x divided by x to the 4th minus 4x squared. So this is the problem, and what I'm going to do immediately is set denominator equal to 0 to find all of the candidates for our vertical asymptotes. And then we do the limit to check them out. So factoring the denominator, it's x squared minus 4 equal to 0. We have x equals 0, x equals to 2, and x equals to negative 2. Are we all good in that? You factor out x squared minus 4 into x plus 2x minus 2, and x squared equals to 0 is just x equals 0. So we have 3 candidates here for vertical asymptotes. 3 candidates. So let's take a look. First, we would like to check if 0 is a vertical asymptote or not. So I will check limit x approaches 0 minus or 0 plus, doesn't matter, check one or the other, of x cubed minus 5x squared plus 6x divided by x to the 4th minus 4x squared. So we're supposed to solve this limit. Since we have these polynomials, we're going to factor them all, and then we are going to cancel as much as we can. So in the numerator, don't forget to write this limit. This limit has to be written over and over again until you get to use it. So we copy the limit, and then the numerator factors into kick out x, and then the quadratic will be factored out into 2 of these. And the denominator we already know is this. So what's happening in the numerator? We have positive 6, so that's going to be negative 3 and negative 2. All right. Awesome. So now, we are supposed to cancel here and see if 0 is the vertical asymptote or not. So x, one of the x's cancels, and we are left with this. Now, if you try to plug in, you see that one x that survives in the denominator still stays there, and it has 0. So it's still dividing by 0. So it is going to be infinity, right? So this is infinity, and we do have vertical asymptote at 0. Now, you might wonder a little bit of how did I decide that if this x minus 3 divided by 0 is infinity? Essentially, what we are going to use as a general rule, even though mathematically it's not correct to write this, x goes to 0 of 1 over x is infinity, and limit x goes to infinity of 1 over x is 0. They're opposites of each other. This is like, it's one of those general rules that you use all the time. And yesterday there was a whole bunch of papers over here. They disappear. Luckily we can destroy one over here. So here's how you can understand, let's say, this one. And if this one is true, then by converse that one should be true as well. This number 1 here is this, one piece of paper, all right? When you start dividing that piece of paper, you are actually cutting it this many times. So if this is number 2 over here, that means that I'm cutting one piece of paper into 2 pieces, which is this, right? Now, what do I get on the other side? What do I get on the other side over here? So if this is a 2, then I get 1/2, and this is exactly a half of the original paper. Now observe that it's smaller, right? So now, if I keep cutting, if this becomes a 4, that means that each one of these gets cut into a smaller piece, and then as we get smaller pieces, you see that if you keep doing this forever, which is this one over here, Remember, this was 2 and then 4 in my case, and then 8 and 16 and so on. So every time I cut, the answer on the other side is the smaller piece of the paper. If I do this forever, what's going to happen with this? Right? See the magic? Nothing there, right? So that is why this stuff works. So that's why when x goes to infinity, meaning you start cutting the same piece of paper infinitely many times, you get nothing on the other end, right? I do this with cookies all the time, it's possible. Now, as you can tell, the other one gets to be the same thing, because as you take one and you divide it by the smaller and smaller numbers, you're actually multiplying them, making larger and larger numbers. So 1 divided by a half is 2, 1 divided by a quarter is 4, 1 divided by an 8 is 8, 1 divided by 1 over 100 is 100. So you see that as this number here goes from 1 into a half, into a quarter, making, right, 1 and then a half and a quarter, they all get closer and closer to 0. As these numbers are going to 0, this number becomes 4, 8, 16, 32, gets to be 100, 1,000, 10,000, 100 million, and so on. So it blows up to infinity. So we see that those ideas are right. So now going back to our problem here, you see that you have the x equals 0, x in denominator, which goes to 0. If x is in denominator and goes to 0, then the answer blows up to infinity. So, and if we have limit, infinite limit, in this case, one of the one-sided limits is equal to infinity. That means we have a vertical asymptote there. Let's go with the next candidate. Limit x approaches 2 from the left. And I will immediately write the factored form. I'm just going to write what survives after cancellation. Now you see that in this case, number 2 you can plug in and you will get values for it. So you will get -1 on top, and you will get 8 on the bottom, right? -1, 8. So not an infinity, which means no VA. We have a hole at 2, -1 over 8. So no vertical asymptote at x equals to 2. And the last candidate for the vertical asymptote is -2. Again, we are writing only what survives here. Oops. And now when you plug -2 in the parenthesis, you're going to get 0 there. Again, 0 in denominator. Again, another infinity, so this one blows up as well, and we have infinity there. So it is going to be a vertical asymptote here as well. So VA at x equals -2. Yes. So out of the 3 candidates in a problem 24, 2 were vertical asymptotes and 1 was a hole. And the one that is a hole is the one that gave us -1 over 8 in the limit. Yes. So, yes, essentially, so what is the answer? Answer is vertical asymptote at x equals 0 and x equals -2. Done deal. And the rest of the problems are the same, just different numbers. So keep pounding on it until it makes sense. Yes? No, but you might want to be cool. Might, I said, not will be or something. It's a level of coolness exhibited by different people. Break time? Sounds like it, right? So I will stop the stream and restart with a new title and a new section.